Speed is not created only by stronger motors. In drone racing, speed is also created by everything the drone does not waste. Every exposed wire, thick arm, raised battery, rough mount, loose strap, and oversized camera forces the drone to spend energy fighting air instead of converting power into forward motion. That is the hidden truth of racing drones. The fastest machine is not always the loudest or most aggressive one. It is often the cleanest, most efficient one. A racing drone may look small, but at high speed it is moving through a serious aerodynamic environment. Air is not empty space. It pushes back. The faster the drone flies, the harder the air pushes against it. This opposing force is called drag, and drag is one of the biggest enemies of racing speed. It slows the drone, drains the battery, heats the motors, increases current draw, and makes the flight controller work harder to keep the aircraft stable. The key point is that drag does not grow slowly. Aerodynamic drag increases very quickly as speed rises. When a drone doubles its speed, the drag force can become roughly 4 times stronger, depending on its shape and flight conditions. This explains why a drone can feel explosive at medium speed but struggle to gain the last part of its top speed. The motors are still spinning hard, but more of their energy is being wasted pushing air out of the way. This is why adding more power is not always the smartest solution. More motor power can help, but it also brings higher battery demand, more heat, more voltage sag, and more stress on the electronics. A drone with lower drag can reach high speed with less effort. That means better acceleration, longer usable power, cooler components, and more consistent performance through the full race. Drag mainly comes from 3 areas: frontal area, shape, and speed. Frontal area is how much of the drone faces the airflow. A bulky frame, tall camera mount, raised battery, exposed antenna, loose cables, and large action camera all increase frontal area. Shape controls how cleanly air flows around the drone. Smooth and narrow parts disturb the air less. Blunt and messy parts create turbulence behind them. Speed multiplies the problem. At racing speed, even small aerodynamic mistakes become expensive. The frame is one of the first places to look. Many pilots focus on carbon thickness and crash strength, but arm shape matters too. Thick square arms may be strong, but they also behave like small air brakes. As air hits them, it separates and creates a turbulent wake. That wake is lost energy. A cleaner arm profile can reduce drag, especially during fast forward flight. But racing drones still need durability. The goal is not to build a fragile drone. The goal is to build a frame that is stiff, strong, repairable, and aerodynamically cleaner. Battery placement is just as important. On many racing drones, the battery is the largest exposed object on the aircraft. If it sits too high or is poorly aligned, it becomes a block in the airflow. A clean battery position helps the drone cut through the air and reduces the throttle needed to hold speed. In racing, the battery is not only a power source. It is part of the aerodynamic body. Propellers are another critical part of the system. A propeller is basically a rotating wing. It creates thrust by accelerating air, but it also creates drag, vortices, and turbulence. Higher pitch props can increase speed potential, but they also demand more torque and current. If the propeller, motor kV, battery voltage, and drone weight are not matched correctly, the drone may sound powerful but fly inefficiently. It may punch hard for a few seconds, then lose performance through voltage sag and hot motors. This is why serious racers test propellers in real flight. They check how the drone accelerates, how it recovers after corners, how hot the motors are after landing, and how much battery voltage drops under load. The best propeller is not always the most aggressive one. It is the one that gives the best balance of speed, control, efficiency, and consistency for the track. Camera angle also affects aerodynamics. A higher camera angle helps pilots see forward when the drone is heavily tilted at high speed. But that same aggressive tilt changes how the whole frame meets the air. The battery, top plate, camera mount, and arms are exposed differently when the drone is pitched forward. A drone should not be judged only by how clean it looks on a table. It must be judged by how it behaves when flying fast, tilted forward, vibrating, turning, and recovering from maneuvers. Motor and rotor airflow also matter. In fast forward flight, the front propellers hit the incoming air first, while the rear propellers may receive air already disturbed by the frame and front rotors. This can affect efficiency and control. Rotor drag and frame drag can also make the drone less precise because the flight controller must constantly correct for unwanted aerodynamic forces. A cleaner drone gives the control system a better platform to work with. This is where drag reduction becomes more than top speed. It improves handling. A drone with cleaner airflow often feels more locked in because it is not being pushed around by unnecessary turbulence. It holds lines better, recovers more cleanly, and wastes less energy on corrections. In racing, precision is speed. A drone that flies cleaner can be faster even without the most extreme motor setup. Pilot technique also matters. Smooth flying is aerodynamic flying. Every sharp correction, unnecessary yaw movement, hard pitch change, or late throttle punch creates extra resistance and wastes energy. A messy pilot can make a good drone inefficient. A smooth pilot keeps momentum, reduces corrections, and allows the drone to move through the course with less drag and less chaos. The fastest laps usually come from controlled aggression, not panic. Drag reduction improves racing speed in several ways at once. It helps the drone accelerate more efficiently. It improves top-end speed because the aircraft faces less resistance. It reduces current draw, which helps control voltage sag. It keeps motors and ESCs cooler. It also improves consistency because the drone can maintain strong performance deeper into the flight. A drone that stays powerful until the final gate has a real advantage over one that fades halfway through the race. But aerodynamic improvement must be practical. A drone that looks smooth but overheats, breaks easily, or blocks signal is not better. Racing drones need cooling, durability, serviceability, and reliable video and control links. Antennas must be protected but still effective. Electronics need airflow. Components must be easy to repair after crashes. Good aerodynamics is not about making the drone look beautiful. It is about reducing waste without damaging reliability. Small details matter. Rough carbon edges, bulky 3D printed mounts, raised screw heads, loose zip ties, hanging wires, and messy tape may seem minor, but together they disturb airflow. A clean build is not only professional looking, it is more efficient. Every part should have a purpose. If an object does not help speed, control, cooling, signal, safety, or race requirements, it may be stealing performance. Weight also connects to drag. A lighter drone usually responds faster and needs less thrust, but if it becomes too flexible, it can vibrate and tune poorly. Vibration forces the flight controller to filter more noise and can make the drone feel less accurate. A slightly heavier but stiffer and cleaner frame may outperform a lighter frame that shakes under load. The real goal is not the lowest possible weight. The real goal is efficient structure. Tuning belongs in the same discussion. A poorly tuned drone wastes energy through oscillations, overcorrections, and bad prop wash handling. Prop wash happens when the drone flies through disturbed air created by its own propellers or sharp maneuvers. If the tune is weak, the drone fights that turbulence instead of cutting cleanly through the course. Good filtering, correct PID settings, solid frame stiffness, and matched propellers all help reduce wasted movement. The smartest racing builders think in systems. Motors, propellers, frame, battery, camera angle, tune, and pilot style all influence one another. A more aggressive prop may add punch but reduce efficiency. A higher camera angle may support speed but make cornering harder. A lighter frame may improve response but hurt stability if it flexes. A cleaner layout may increase speed without demanding more power. Every change has a trade-off. That is why drag reduction is so powerful. It compounds across the entire race. Less drag means easier acceleration. Less drag means lower current demand. Less drag means cooler motors. Less drag means stronger battery performance. Less drag means better line control. One improvement may look small, but many small improvements across the drone can create a serious racing advantage. The future of racing drones will become more aerodynamic and more data-driven. Builders will pay more attention to frame shape, battery integration, propeller efficiency, cooling airflow, and flight log analysis. Racing drones will still need to survive crashes, so they will never become fragile wind tunnel sculptures. But the fastest designs will increasingly be clean, stiff, efficient, and optimized around real flight behavior. The main lesson is simple. Air is not empty. At racing speed, air becomes resistance, and resistance becomes lost speed. A beginner tries to overcome that with more throttle. A better builder reduces the resistance. A better pilot flies smoother lines. A serious racer does both. So before upgrading motors, look at the entire drone as an aerodynamic system. Look at the arms, battery, wires, camera, props, antenna, mounts, frame stiffness, and tune. Every exposed edge is a question. Every bulky part is a tax. Every messy airflow path is stolen speed. Drone racing is not only a battle of power, it is a battle against wasted energy. The drone that wastes less energy fighting the air has more energy left for acceleration, precision, and victory.